be defined, and for this Cauchy integral theorem is valid. Correct? For this Cauchy integral theorem is valid. So I will write this Cauchy integral theorem as 1 over 2 pi I over this contour f of z by z minus z naught dz. Okay, so maybe I will write it in this fashion. I will put this as z prime, this as z, and I will call this as z. So dz prime. So what should I write here? This should be f of z, right? Wherever z naught is there, I put z. Okay. Now I am going to rewrite this. This is just a manipulation. So let me write this as integral over x close to curve f of z prime divided by z prime minus z naught plus z naught minus z. So I am going to multiply and I am going to add and subtract this z naught. So this is z prime minus z naught and z naught minus z. There is no change, right? This is still the same as that. Now z prime is, so z prime, this is an integration variable, right? So I think I must, integration variable is on the contour. Integration is over z prime, so integration variable is on the contour, right? It's a contour integral. Z is in the interior of this contour. So note here that z minus z prime, z minus z naught is modulus of this value is less than z prime minus z. Z prime is on the contour, z is in the interior, so distance between z and z naught is smaller than distance between z prime and z. So I will write it in this fashion, minus z minus z. So I will rewrite this as f of z is equal to 1 over 2 pi I integral over the contour. I will pull out f of z prime divided by z prime minus z naught into 1 minus z minus z naught divided by z prime minus z naught. Now you can see here, since this is less than this divided by this will be less than. Correct? This implies z minus z naught modulus divided by modulus of z minus z prime minus z naught. So now I can write this as 1 over twice pi I integral over a closed contour T. So I can write this as f of z prime by z prime minus z naught into 1 minus z minus z naught divided by z prime minus z naught to minus 1. Now this one can be expanded in binomial series, and this will convert if the modulus of this one is less than 1, which is the case according to what we have considered. So I can write, so what is the expansion? 1 minus x minus 1 is equal to 1 plus x plus x squared. So if I use that expansion, then I can have 1 over pi by I integral over the closed curve C f of z prime into sum over n is equal to 0 to infinity z minus z naught to the power n divided by z prime minus z naught to the power n plus 1. Why n plus 1? Because there is something here. Okay, now I can interchange summation and integration and then write this as sum over n is equal to 0 to infinity z minus z naught. This is something which does not depend on the integration variable. Integration variable is z prime. So z minus z naught to the power n I will pull out and then write this as 1 over 2 pi I integral over the closed contour f of z prime divided by z prime minus z naught to the power n plus 1 dz prime. But what is this quantity? We have already shown here, that is nth derivative of f. So this is actually the Taylor series, is equal to sum over n is equal to 0 to infinity f nth derivative at z naught into z minus z naught to the power n. I am sorry for this, but f nth derivative of f to z naught to the power n. So this is Taylor series. So a function which is analytic can be expanded in Taylor series.
This derivation, is this function analytic and proposal?
Should be at the point z. F of z is analytic inside this. F of z is analytic. That is our Cauchy integral theorem proof of it. F of z is analytic, but f of z by z minus z is not analytic at z. That is okay. But f of z is analytic. Only when it is analytic we can expand. One point that we have to worry about, any analytic function, so f of z is analytic, f of z is analytic at z equal to z naught, then f of z can be written as n is equal to 0 to infinity 1 over factorial n f to the n of z naught into z minus z naught over n. This is Taylor series. Now this series will be converging only in some region, not that it converges everywhere. Correct? This series will converge to this only in some region. Correct? For example, 1 by 1 minus z, if this is the function, then you write 1 plus z square, etc., etc. This will converge. Okay, this function is function is analytic at z equal to 0. So I can expand this around z equal to 0. This is the function. This converges. So this series, the series in the right hand side converges for z within the unit circle. This not z less than 1. It will not converge for points that are outside. So there is something called radius of convergence for Taylor series expansion. So there will be only some region in which, so if it is analytic at that point, you can expand it in Taylor series. That Taylor series will converge only in some region around that. It will not converge everywhere. For example, in this case, this series will converge. So if you have this complex plane, you are expanding it around this point, and you have a unit circle. For every point in the unit circle, this series will give you converge to this function. Or this function can be expanded. So we have to ask a question that if you expand a complex function at a point where it is analytic, but the Taylor series converges in some region around that point. So you have to be careful whether we are actually taking. There is also a nice way of doing something like this. Let me just, for example, this 1 by 1 minus z, instead of expanding around z equal to 1, if I expand, let's say z equal to, so z equal to 0, I expand it to z equal to 0. But if I, for example, expand it at z equal to half, let's say, so this is our unit circle. Okay, so that means I'm going to write this as 1 by okay, so let me put it this way. Okay, maybe I will just come back to this when I discuss it. What I am trying to say is, it is possible that we can extend the analyticity, or we can expand this region to other regions in the convolution. This is called analytic continuous. We will talk about it in detail when we discuss it later. So it is possible to extend it to other regions complex plane by using what is called analytic. Okay, so this is about the theorems that we know on analytic functions. So just before I sign off this topic, let us just summarize what we have done in this topic. So f of z is analytic in some region this is something that we know. If we know that we have a function that is analytic in some region R, then first result that we have is that over a close to contour f of z is 0, and then we had second result that over a contour 1 over z plus n dz is equal to 2 by I delta n comma 0. And third, we had integral 1 over 2 by I into integral over the closed curve f of z, where z minus z naught, d is z naught, d z is equal to f of z naught. And from here we were able to write that n derivative by integral over a closed curve f of z divided by z minus z naught to the power n plus 1 dz, and then we were able to write down f of z as a Taylor series expansion of 0 to infinity 1 over factorial n into f n derivative at z naught into z minus z naught to the power n, and the right hand side convert this to f of z in some region around z. So these are kind of summary of results with the analyticity that we have. So essentially this last point is that, this last point essentially means that if you have points that are not here, there will be some point here such that the Taylor series will converge to all points such that some z1 minus z0 is all points will converge, points which are inside this, the Taylor series will converge to points. That means there exists, so let us call this as some radius. Radius r such that z minus z0 less than r. Okay. Z minus z naught less than r, Taylor series. So this r is called the radius of convergence. Only for those values of z which are inside this, which will satisfy a z minus z naught equal to less than r, this Taylor series will converge to zero. That is the meaning of this last point. RHS converges to f of z in some region around z. So there will be an upper bound on the radius. That if I take from here, if I take integral over a closed curve f of z, what will I get? I will get sum over n is equal to 0 to infinity 1 over n factorial f n of z naught into integral over the closed contour z minus z naught to the power n d. But what is this value? What is this integral? Here remember, here n is greater than or equal to 0. Correct? And we had this already. Correct? This can also be written as integral over a closed closed curve, this is integral over a closed curve around origin. But if I have an integral over closed curve around z naught, I can write this as dz by z minus z naught to the power n plus 1. So this result is also true for this if you take this contour around z. Correct? So now you know if n is equal to greater than or equal to 0, this is 0. This is actually Cauchy's integral theorem. Cauchy's integral theorem says if f of z is analytic, then integral over a contour f of z dz is 0, which can also be seen from here in this contour f circle z naught less than z naught to the power n because it is correct. So from the Taylor series expansion, you can see the same result from different angles. In the following way, we have for any analytic function a Taylor series expansion. At least in some region, within some radius of convergence. Supposing we have, suppose if I have an f of z, which already has n is equal to 0 to infinity. So a n z minus z naught raised to 1. A n is nothing but f to the n by f factor. Okay, so that is, we already know if f of z is analytic, we can write it down. But in addition to this, if we have some terms like this, from a minus 1 divided by z minus z naught plus a minus 2 divided by z minus z naught whole square and so on. If I have something like that, that is the expansion of a function is having some terms which are negative exponents of z minus z. Now one thing immediately that I can notice is that if I take an integral over a closed contour f of z dz, if I take an integral over a closed contour f of z dz, then using the result that we have already shown, so using this result, an integral over a closed contour dz divided by z minus z naught to the power n plus 1 is 2 pi I into delta n comma 0. That means you have to take an integral over each term. Integral over this thing we have already said is 0. Integral over all these things are also 0 except this one. So you will get result which is a minus 1 into 2 pi. Correct? So this a minus 1, which is the coefficient of 1 over z minus z naught is called residue. This is called the residue. So the integral is simply 2 by I times the residue of the function z equal to residue of f of z, right? Now interestingly, you can see that this series convergence requires z to be above some radius. be above some radius. Suppose if you define this 1 by z minus z naught as some complex number w, then it will be a power series in w, correct? W plus w square plus w cube. That requires, convergence requires w minus w naught should be less than some radius. That means z minus z naught should be greater than some radius. So you can see in the complex plane, you can have a situation if you have z naught here, there is some r for which, let's call this as r1. So n is equal to 0 to infinity, a n z minus z naught to the power n converges for modulus of z minus z naught less than r1. Now if you consider another variable r2 such that sum over n is equal to minus infinity to minus 1 a n z minus z naught to the power n converges for modulus of z minus z naught greater than 1. That means all these negative powers will converge in this region, positive powers will converge in this region. So there is no region in this case where both will converge. But we can.
What about the other region?
Yeah, so that region both will not converge. Right? But we can have a situation, slightly better situation, where we call this as R2 and this as R2. So that means the negative series will converge beyond this, positive series will converge in this. So in the annular region, both will converge. In the annular region, both will converge. That means when you have a series, if you have a function which gets expanded in a kind of series like this involving negative powers, the convergence is always only, the region of convergence is always an annular region. But you can have a situation where this R2 becomes 0 and R1 becomes infinity. In which case, you can have convergence in the entire complex plane. But even if it is one point, that is a point where it cannot converge. So you can see that convergence between convergence of this series and this series together to a complex function requires the region of convergence to be an annular region. We can actually develop a similar mathematical derivation like Taylor series, but let me just see if I can. So another 15 minutes. So the mathematics is exactly similar. So if you look at Afton's book and mathematical physics, you will understand the derivation. So I will not do the derivation. And this series, so f of z is equal to sum over n is equal to minus infinity to plus infinity a n z minus z naught to the power n is r n. What is the difference between Taylor series and Lorentz series? You can expand Taylor series, you can expand a function in Taylor series only if it is an analytic function. But Lorentz series expansion can be done even if the function is not. So we have we have different kinds of singularities. Okay, so we will next talk about types of singularities. You call a function singular at a point if it goes to infinity at that point. Okay? It's not finite. For example, if you have some function, so there are different types of singularities. I will give you some examples of this type. The first one that I will talk about is removable singularity. Basically, if you look at the function, it appears there is a singularity, that's not a singularity. Let's consider an example like this. F of z is equal to sin z by. It appears z equal to 0 goes to infinity. Correct? But if you actually look at this, it is 1 over z into, we expand this sin z minus z cubed by factorial 3 plus z power 5 by factorial 5 and so on. So you can see that this is nothing but 1 minus z square by factorial 3 plus z to the 4 by factorial 5 minus and so on. It never goes to infinity. As z goes to 0, it is 1. So this is actually analytic. So such singularities which can be removed by looking at the expansion. So you can see that this is actually a Taylor expansion. There are no negative powers of z. But if we take a function like this, sin z by z square, sin z by z square, we have in this, it is 1 by z minus z square by z by factorial 3 plus z cubed by factorial 5 and so on. So you can see these are all positive powers of z, but there is one negative power. Correct? So it is singular. So z equal to 0 is a singular or a singular. Z equal to 0 is a singular. And as I have shown you here, once you write this Rn series, integral a closed curve of f of z dz is nothing but 2 pi I into a minus 1, coefficient of 1 over z by z. That is the residue. So what is the residue of this function? So I will simply write this as residue of this function at z equal to 0 is 1, because it is 1 by z. Now how do we calculate this in general? Is that you multiply this function by z and then take z going to 0. So in general, residue at z0 is nothing but limit z minus z0 into f of z in the limit z tending to z. This is how we can find out residue. So in this case, if z is equal to 0 in this example is called a pole or a simple example, if I take f of z is equal to sin z by z cube, then I will have 1 by z square minus minus 1 by factorial 3 plus z squared by factorial 5 and so on. Here also we have negative powers. Correct? We have negative powers. But what is the residue? Residue is 0 because we don't have 1 over z. Correct? So residue of this one, that is equal to 0, is 0. If we write like this, suppose I have a function f of z which is equal to a minus 1 divided by z minus z naught into plus sum over n is equal to 0 to infinity a n into z minus z naught for n. This is the regular part of the Taylor series expansion and is the only term that I have. And we say that this system has a simple pole. Okay. So f of z has a simple pole and then the residue r at z naught is equal to z minus z naught multiplied by this. Take the residue. So the coefficient.